So we all know, there are different types of hydrocarbons, starting from alkane, with a general formula of CnH2n plus 2, which means it has the maximum, hydrogen number for a certain number of carbon, right? And is also called saturated. So meaning of saturation means there is no double bond. So it has the maximum number of hydrogens. All of them are single bond, single CC bond, single CH bond. And obviously, the hybridization of the carbon in the alkanes are sp3 and with around 109.5 degree of bond angle, right? We can talk about DBE later. And for alkene, alkyne, and benzene, all of those have unsaturated bond, either CC double bond, CC triple bond, or some other organic compounds have CO double bond, CN double bond, so they are also called unsaturated. So we can briefly show the functional group of the alkene, which is the CC double bond. So which means there are 2 hydrogens less than the saturated alkanes, right? So once there is a double bond, there are 2 hydrogens less. So the formula, the general formula for the the mono alkene, which means there is only one CC double bond, should be CnH2n, right? So no 2n plus 2. And similarly, these 2 carbons connected by the double bond should be sp2 hybridization. And the bond angle is supposed to be 120, right? I think those are relatively straightforward, so it will be a little bit fast. And alkane, there will be a triple bond, right? And similarly, there will be 2 less hydrogens, and the hybridization will be sp, right? And bond angle will be 180. So we are focusing on the the CC double bond and the CC triple bond in alkenes and alkynes, right? Don't ask me why it's called alkane, alkene, and alkyne. To be honest, when I first learned this in English, it's also confusing to me. Benzene, based on the suffix, is kind of similar to the alkene, right? And actually the structure is also quite similar. But you probably know the properties are very different, right? It's more similar to the alkane rather than the alkene, because it cannot discolorize the bromine water just like the alkene. So you can see the formula is C6H6, right? And probably we can write down the resonance to show all of the CC bonds, all of the CH bonds are the same, and all of the bond angles are 120, and all of the hydrogens are sp3 hybridized, right? And if we want to get a general formula, actually it can be CnH2n minus 6, because there is 3 double bonds and 1 ring, right? The ring, oh, thanks, sorry, yeah. Sometimes, my mind is not on the same page with my hands. So it's CnH2n minus 2. You can see there are 3 double bonds and 1 ring. A ring actually also will decrease the hydrogen number by 2, because when you need to put the head of the snake and the tail of the snake together, you need to cut something to put these 2 carbons together, right? So there will be 2 hydrogens less. And so the next very, very important concept I want to introduce is the DBE. The full name is called double bond equivalent or equivalence. There are a few similar names, such as the degree of unsaturation. So basically it means the number of molecules of hydrogen that would have to be added to the molecule to convert all of the pi bonds and the rings into single bonds. So basically it's kind of how many pair of hydrogens the molecule is missing, right? So 1 DBE can be 1 double bond. Double bond. Not necessary to be CC double bond. It can be CO double bond. It can be CN double bond, right? Any double bond you can think about. And if it's a triple bond, what will be the DBE for 1 triple bond? It should be 2, right? So 1 triple bond is not 3, right? It's 2. It's just 2. Keeping this in mind. And or one, oh, I think I should put a double bond here and put the ring here. So either one ring or one double bond, right? So the triple bond has a dBe of 2, dBe, right? So basically, if we get a molecular formula, how can we calculate the dBe? For example, if I get CXHY, how can we calculate dBe? Yeah, go ahead. Xiang'an? Okay. But if we only have the molecular formula, how can we know what kind of bonds are in the structure? And for the dB calculation, actually, we do not care about what kind of bonds are there. We just want to know how many hydrogens are missing. And then based on the dBe, we can further analyze what kind of bonds are possibly in the structure, right? Yeah. Yeah. So if we have a formula like this, does this make sense to you? If we say the dBe is 2x plus 2 minus y divided by 2. So what is the 2x plus 2? Yeah. Yeah, so if it's alkane, the maximum hydrogen number it should have, right? And now we're using minus y, that's the difference between the number of hydrogens it has now with it is supposed to have if it's saturated. And then we divide it by 2 because we are counting the pair of hydrogens, right? Kind of how many pair of hydrogens are missing. So if we make it slightly more complicated, let's say it's CXHY and there is a halogen. Let's say the halogen, there are Z halogens in the molecule. So can we get a similar equation to get a dBe? I think we definitely can, right? So the number of the hydrogens is still the same, right? But when you count how many hydrogens this molecule is having right now, you may need to consider the ZX, the Z halogens, because those halogens actually replace the hydrogens, right? So this is why we need to minus Y plus Z and then divide it by 2. Does this make sense to all of you? Let me know if you have any question. Thank you. And then we can make it a little bit more complicated. So now say if you have oxygen, so what would be the situation? Let's have a look at the structure. Let's say ethanol, CH3, CH2OH. Obviously we know, it is made by all single bonds. So the dBe is supposed to be 0, right? So we try to use this to, figure out what would be a good equation for calculating dBe. So it seems like it should be 2x plus 2 minus y divided by 2 because there are 2 carbons and 6 hydrogens, just C2H6, right? So based on this, it seems like we didn't care about the number of oxygens. So why does this make sense? Let's try one more molecule. So now say it's acetaldehyde, CH3CHO. The molecular formula will be C2H4O. If we still use the same idea, 2x plus 2 minus y divided by 2, we got 2 times 2 plus 2 minus 4 divided by 2. We got 1. This is exactly, the same as the double bond, right? It is 1, and there is 1 CO double bond. So it seems like, based on our few examples, we don't need to care about the number of oxygen when calculating the dBe. So why this makes sense? So oxygen actually has 3 ways in bonding. The first way is just put in between a carbon and a hydrogen, which is an alcohol or a phenol, right? So obviously, this is kind of an insert. You insert the oxygen into the CH bond, so it won't affect the dBe, right? And another way is you insert the oxygen in between 2 carbons. So this is the ether. So similarly, the number of oxygen won't change the dBe. It will not affect dBe, right? And another way probably will have a CO double bond. And when the O is double bonded to the carbon, you probably realize there was two hydrogens before the oxygen is binded, right? So which means the number of the oxygen double bonded to the carbon actually is reflected by the decreasing of the hydrogens in the formula. So this is why no matter what is the way for the oxygen to bind with the molecule or bind in the molecule, when we calculate dBE, we don't need to care about the number of oxygens. So I will leave one question for you to think about. If we have nitrogens in the molecules, so how can we calculate dBE in that case? So I think you can follow the similar idea to try to figure out, but I don't have the time for you to think about it right now. So leave this as your practice problem for homework, okay? Probably you don't like me. Oh, this is the Friday, USNCO coaching session. You even assign homework. Okay, so with the concept of dBE in mind, we can talk about how to count the isomers. First, you guys all know isomers are molecules with the same formula. More specifically, we should say molecular formula, but different structures, right? And here is a brief summary of different types of isomers. We try to classify the isomers, and then this kind of classification can help us to count, even to draw all of the isomers for a certain molecule. Right? So first we can put them into two big categories. The left one is called structural, another one is called stereo. What's the difference? Structural means they have different connection. So different connection. We can show what is the meaning of different connections later. And another one is called stereo, which means they have the same connection, but they have different three-dimensional arrangement. Let's have a look at a few examples. For example, the butane and the methyl propane, which is also called isobutane. Isobutane. So you will see, the carbons are connected in a different way. So this is why it belongs to the structural isomers, right? And more specifically, we can call it, chain isomer or skeletal isomer because they have a different, carbon chain or different carbon skeleton. Makes sense, right? And could you please, think about these two isomers, the but2-in and the but1-in, right? Oh, this reminds me of a joke, something like, a diene is triene. The diene here actually is not diene, right? It's just, there are two CC double bonds, it's called diene. And if there are three double bonds, it's called triene. Okay, so what can be a good name, for these two isomers, since they have the same chain, right? The chain is the same. 4 carbons in a straight chain, no branches. But you can see the position of the CC double bond actually are different, right? What can be a good name to summarize? Can we just call it, positional or position? Makes sense, right? And then the last one here, but-in, but2-in, and cyclobutane. So the first one is a double bond, another one is a ring. So they have the same dBE, right? So they have the same, number of carbons. They have the same number of hydrogens. They are isomers. So this one is a little bit abstract. We can call it, they have different function groups. We can call it functional or function. So basically they have different function groups. For example, the alcohol and the ether with the same number of carbons can be called functional isomers, right? So all of those three are having different structures, different connections. So this is why they are called structural isomer. Another one, let's have a look at these two. The top one is a CC double bond with 2 chlorine. The second one is also a CC double bond with 2 chlorine. But you guys know, the CC double bond cannot freely rotate, right? Due to the pi bond. So there are two p orbitals, parallel to each other. So this double bond cannot, like the sigma bonds to, freely rotate. So this is why these two molecules cannot, change into each other without energy input, right? You may have to put in energy to break the bond first, at least break the pi bond, and to rotate in this way, and then finally, overlap or, parallel in a different direction. Sorry, my body is not so flexible. I cannot, show you the idea. But probably I can use this, right? Maybe this one is better since, I have a blurring effect. So like this, and then you break it. So they are perpendicular to each other right now. And then finally it rotates in this way and, overlap in the opposite direction. So the double bond is still there. So anyway, so these two structures are different. So we call this into cis-trans or ZE. But I think cis-trans probably makes a little bit more sense to you because trans, which one would be trans, guys? Trans means different, right? Yeah, the word I can think about, yeah, they are in different direction. The first one can be called trans. The first word came to my mind is transformer. I probably watched the movie too many times. Right? So they are in different sides. So this one is called cis. I forgot, what is this name from? Probably from Latin or Greek, right? There must be a reason why it's called cis. But probably it doesn't make too much sense to us, if we just know English only, right? So anyway, cis is the opposite of trans. So you may have to know the difference. So this means they have the same connection, but they have different, 3D arrangement. So this actually is a 2D arrangement because both of these two molecules are planar, right? Another one is when one carbon is connected to 4 different groups. As you can see, these two structures. And you try to rotate one of the structure and try to make it overlap with the left one. Or more specifically, is to make them superimposable. And then you realize it's impossible. It's just like our left hands and the right hands. So you can do it this way, but actually they are not fully overlap. This is not called superimposable, right? So these two structures actually are not the same. And they have different optical properties. We don't want to talk too much about, what is the optical property. Basically, they can rotate the single polarized light into different directions. So we call them, optical isomers because they have different optical properties. Oh, by the way, sorry, this is not, they are called cis and trans, but the type of this isomer is called geometric. Maybe it's just because it's related to a two-dimensional world. So this is why we call it geometric. So, and the optical one also have another related name. It's called chiral. Chiral. So this chiral is related to the hands. So the CH here, is not called, chiral. So CH has a pronunciation of K in some words, right? I was told by my student it's called chiral, not chiral. Okay. And the opposite word is called achiral, right? Achiral. So with this in mind, we can try to work on one practice problem. So our goal is to draw all of the isomers of C4H8. I want to show you the logical chain first because we still have chance to work on the practice problems later. So the first step, actually the most important step, which is also easy to be forgot, is to calculate the dBE. I can explain later why we need to calculate dBE. So we just follow the formula 2x plus 2 minus y divided by 2. So you will see, actually it's 1. What does it mean? Which means there is either a CC double bond or a ring. So this is why I urge you to calculate dBE first. Because if you just try it, and you probably draw a lot of structures which are completely saturated, so it's totally wrong. starting from the beginning, it is wrong. And you probably realize that after 10 minutes of joining, right? But you didn't do any work, but direction is not right? So if we know the dB is 1, and then we can analyze, oh, there are two possibilities for the function groups, either an alkene or a cycloalkane, right? And then in each category, we can further analyze. First, we want to figure out the chain isomers. So it can be a straight chain, it can be a branch chain, right? So if it's a straight chain doesn't mean it's linear, because we know, all of them has a sp3 hybridization, a tetrahedral structure, right? So this is called a straight chain, but it's not linear, and it can be like this, right? I think it's easy for you to understand. This is not called a branch chain, right? It's still, the straight chain. So it's the same as the first structure. And then we can further put the function group in a different position. So we can either put it here, we can also put it here, right? Do you need to think about to put it here? We don't need, right? Because this one is the same as the last one, right? Because the structure is symmetric. So you just need to flip it over and you got the last one. So we got two positional isomers in the branch chain, the straight chain. And then in the branch chain, and we also add double bond. Next we add it here, and you realize the central carbon is also symmetric. So you don't need to put it here, you don't need to put it here, because they are all the same, right? So let's follow the similar idea to the cycloalkane. We can also have a 4-member ring, carbon, carbon, carbon. Oh, by the way, I didn't join any hydrogens, but you can realize there are a certain number of hydrogens on each carbon, right? Different numbers. It depends on how many bonds it already have for each carbon. And another possibility is 3 carbons, but there is a methyl group in a certain position, right? So this is also similar to the straight and the branch. Basically, they have different chains, right? Or you can say they have different rings. And the last thing we can think about is the stereoisomer. Is there any structure we listed here? 1, 2, 3, 4, 5. Is any of this structure having stereoisomers, including cis, trans, geometric, or optical? The compound 1. Yeah, the compound 1, the double bond in the middle, and we have 2 methyl group on the double bond. So we can put these 2 methyl group on the same direction of the cis double bond. We can also put them in the different direction of the double bond. So obviously, these 2 are different. This one should be called trans, and the last one should be called cis. So we finished the work. And you can check all of the other structures to see is there any other molecule either having a chiral carbon or having some other stuff, right? But after we check everything, I think that's it. So the only possibility you may need to analyze is this carbon chiral or not, because this is the most likely chiral carbon, right? Because it kind of connects to a lot of different groups. But I actually realized if you go from this way and you go from that way, these 2 actually are symmetric. They are the same. So it's not chiral, right? So we have a practice problem here, slightly more complicated, but not too hard, from the National 2018 Part 1. Would you like to take maybe let's say 2 minutes to think about this? You can also choose to annotate on my screen if it's convenient for you. Thank you. Yeah, I cannot, enable the the polling function today, so you guys can just work on it, and then later we can have a brief discussion. Oh, thanks. It's automatically jump out. Who helped me? Thank you. Oh, this is wonderful because I can also submit my answer. I never got this opportunity. I always be the host. Yeah, I'm trying to understand your work. So you got the DBE1, and you classify them into chain and branch. Yeah, and you don't need to think about the cyclic structure because they call acyclic, which means the ring structure, don't need to be considered. So this actually simplifies the work, right? Okay, you already got an answer. Let me try. So as you show, DBE is 1, and chain and branch. So for the chain structure, there are 5 carbons, so it's slightly more complicated. For the branch structure, we can get this one. How about this one? They are the same, right? It's the same as the first one. Yeah, so we don't need to consider this one. And there is another, branch situation, right? Actually, you are working on decreasing the number of carbons on the main chain. What is the main chain? Is the chain with the most number of carbons, right? So you decrease from 5 to 4 to 3. So this is why you have 2 carbons left, and then you need to think about how to put these 2 carbons. And then now it's time to add a double bond, right? Because now we already finished, the chain isomers. The next step is to think about the positional isomers. So we can put it here. We can put it here. That's it, right? Only 2. Because if you continue to go to the right side, they are the same. They're symmetric, right? So there are 2 here without considering the stereoisomers. And then we go to the right side, double bond here, double bond here, double bond here. And when double bonded here, these 2 are the same, right? Because this part is symmetric. So we have 3 here, we have 2 here. Make sense? And then let's continue. We add, this is the same, so we don't need to consider. And then we try to add a double bond here. And then boom, the central carbon explodes. There are too many carbons. There are too many bonds, right? It disobeys the octet rule. There's no carbon, can have 5 bonds unless it's in the transition states, right? So there's no alkene, from this chain or from this skeleton. And then it seems like we should choose C, right? But this is the national question, right? So we may need to further think about any stereoisomers, right? Is there any structure with stereoisomers? Which one? You mean when the double bond is here, right? 2-pentene. So let's try it. So we have 1 methyl group. In the right side, we have a acyl group, and then we have 2 hydrogens, right? So now I think it's clear for us to see, when you put the acyl group, flip with the hydrogen, these 2 structures are different. They are cis and trans. And you probably can work on the other, alkenes as well to see whether there are any, trans or cis structure. You can further think about is there any chiral carbon or not. So the answer finally is 6, right? But I'm not encouraging you to choose the one with the most answer, okay? But if you have no clue, maybe you can try. Okay, I think I already used a lot of time, so we can leave this question as your homework because we didn't talk about example with chiral carbons. So this will be an example for you to think about chiral carbons probably, or maybe not this one, but you definitely can find more examples with chiral carbons, and then they have the optical isomers. Okay. Yeah, that's all I would like to share with you today. And any last minute question before I transfer to Coach Aaron Yang? You mean kind of how can I quickly differentiate? Oh, when you put double bond in different places, they are different? Yeah, there are different ways. A simple way is like what I shown here. You just draw the line, and you don't need to be fast like me. So you can try in this way, right? You add a double bond here, and you draw another structure, and you double bond here, and then you draw again, and you compare those structures to see which are the same, which are not, right? But your goal, your logical idea is you try all of the 4 positions, right? And then you compare which are the same, which are not, right? So when you try a few, maybe 2 to 3 practice problems like this, you will get a sense, right? You don't have to draw all of them out, and you will quickly see, oh, this one is different from that one, and that one actually is the same as the third one, right? So yeah, practice makes you perfect. It works in any subject, including the chemistry Olympiad. Okay, I'm done. I will stop sharing my screen.